Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. Uh, this article would be the last article of chapter 4, and in this chapter, we have been talking about trusses. We have learned how trusses are formed. We have learned what is a plane truss. We have learned what is a space truss. From there, we have found out two techniques to find the forces within the members. Number one, method of joints. Number two, method of sections. We went through certain examples. One of the last form of for mechanical engineers in structural designs are the development of frames and development of frame mechanics or machines. Now, frames are very important part of our systems. So the question is, how do you define a frame? A structure is called a frame or machine if at least one of its individual member is a multi-force member. So the question arises, what is a multi-force member? A multi-force member is defined as one with three or more forces acting on it, or one with two or more force and one or more couples acting on it. Now, frames are structures which are designed to support applied loads and are usually fixed in positions. Machines, however, are structures which contain moving parts and are designed to transmit input forces or couples to output forces or couples. Because frames and machines contain multi-force members, the force on these members in general will not be in the direction of the member like a two-force members. So we cannot directly analyze the structures by the methods developed previously, like method of joints or method of section. The methods apply to simple trusses components. So now we are going to talk about a understanding of interconnecting rigid bodies. Now we discussed in the past chapters the equilibrium of multi-force bodies are concentrated on the we concentrated on the equilibrium of single rigid body. Now, in the present, our focus will be on the equilibrium of interconnected rigid bodies, which includes multi-force members. Most Although most such bodies may be analyzed as two-dimensional systems, there are numerous examples of frames and machines which are three-dimensional systems. You see these things in your daily life. The force acting on each member of a kinetic system are found by isolating the members with free body diagrams and applying the equation of equilibrium. The principle of action and reaction must be carefully observed when we represent the force of interaction on the separate free body diagrams. Now, if the structure contains more members or supports than are necessary to prevent collapse, then, as in case of trusses, the problem is statically indeterminate, and the principle of equilibrium, though necessary, are not sufficient for a solution, although many frames and machines are statically indeterminate. Now we will consider only those here in this chapter. We will consider only those which are statically determined machines. Now, if the frame or a machine constitutes a rigid body, a rigid unit by itself, you can say a frame is considered rigid by itself when removed from its supports, as shown here in figure A. This A frame, the analysis is began by essentially all the force external to the structure treated as a single rigid body. Now, we then dismember the structure and consider the equilibrium of each part separately. The equilibrium equations for several parts will be related through the terms involving the force of interaction. Now, if the structure is not rigid and is not a rigid unit by itself, but depends on the external force support or for rigidity, as you can see in figure B, then the calculations of the external support reaction cannot be completed until the structure is dismembered and the individual parts are analyzed. Simply put, if you can see figure A, the member connecting the two limbs, if you remove the force P, the structure itself is going to be rigid It's non-collapsible structure because force P is not changing anything of the rigidity of the structure, but in B, P is affecting the rigidity. When you remove it, it is going to collapse. It's going to act like a scissors. Now, how do you represent these forces in a free body diagram? So this is an important part again. So what do we do when we take these machines and represent it in a free body diagram? In most cases, the analysis of frames and machine is facilitated by representing the force in terms of the rectangular components. Now, this is particularly so when the dimensions of the parts are given in mutually perpendicular directions. The advantage of this representation is that the calculation of moment arms are simplified. In some three-dimensional problems, particularly when moments are evaluated about axes which are not parallel to the coordinate axis, we use vector notation to its advantage. To use the vectors advantage, we can use simple vector analysis for the advantage. Now, it is always possible to assign proper sense for every force or its components when drawing the free body diagram, and it becomes necessary to make an arbitrary assignment. In any event, it is absolutely necessary that a force be consistently represented on the diagram for interacting bodies which involve force in question. So, two bodies connected by a pin A as shown here. The force component must be consistently represented in opposite direction on the separate free body diagrams. For a ball and socket connection between members of space frame, we must apply action-reaction principles to all three components. All three components. Now, the assigned direction may prove to be wrong when the algebraic signs of the components are determined upon calculations. Now, if AX, for instance, should turn out to be negative, it is actually acting in the direction opposite to the originally represented. Accordingly, we would need to reverse the direction of the force on both members and reverse the sign of its force in terms of equation. Or we may leave the representation as originally made and the proper sense of the force will be understood from the negative sign. If we choose to use vector notation in labeling the forces, then we must be careful to use a plus sign for an action and minus sign for a corresponding reaction. We may occasionally need to solve two or more equations simultaneously in order to separate the unknowns. In most instances, however, we can avoid simultaneous solution by careful choice of the members or group of members for the free body diagram, and a careful choice of moments axes which will eliminate undesired terms from the equation. The method of solution described in the illustration above, we are going to look at the problems which will help us further understand.